So welcome to week 8 of course Combinatorics 2 at Stockholm University, and I hope you're as excited as I am that we start with a new and fresh topic, namely graph theory. And so graph theory is a really fascinating area of mathematics because most of the definitions are really easy to understand. So everything seems to be very elementary, and also the statements and results. But actually, some of the proofs are really, really very, well, how can I say, kind of difficult and tricky. But, and so at the same time, this area has lots of applications. And so it's really a lot of fun. So let's start here by defining what a graph is. And I will go quite quickly through this because this is something you should look up by yourself. So read the book, look up the definitions, and really find out what the precise, definition is of these words. So what is a graph? So here I drawn a graph. A graph consists of two data, namely we have the vertices and we have the edges. Okay, so what are the vertices? Well, the vertices are 1, 2, 3, and 4. So this is the vertex set. So this graph has 4 vertices. What about the edges? Well, 1 and 2 are connected, 2 and 3 are connected, and so forth. So let's write this down. So they have 1 and 2. 1 and 2 are connected, 2 and 3. 3 and 4. So 2 and 4 are connected, and 1 and 3. And that's it. These are the edges. So what is important here, first of all, so what we see is that an edge is an unordered pair of vertices. So unordered means that it doesn't really matter which way around here. So the only important thing is that 1 and 2 are connected. And the other important thing you see here is like it doesn't really matter how you draw it at all. You know, you can do it like this or in any way you like. In fact, you don't even have to be able to draw it in any way. This is an abstract notion. It's nothing to do in the way how you draw it. It's just the only thing you have to know is you have a set. So these are the vertices. And you have to know whether 2 of these vertices are connected by an edge or not. That's the only thing you have to know. That's what makes a graph. Okay, so what kind of definition do we have? For instance, there's a notion of adjacent vertices. That's just a different word for we have 2 vertices that they are connected by an edge, means that these 2 vertices are adjacent. Then incident edges, what does that mean? Well, if you have an edge and that, let's say 2 and 3, well, what you say is 2 and 3 is incident to 2, to the vertex 2, because 2 is a vertex of the edge. So every edge is incident to 2 vertices. Then isolated vertices, what's that? Well, in that graph there is no isolated vertex, but assume we would add this vertex here, well, then this vertex is called isolated because it's not connected to any other vertex, so it's not in any edge. So finally we have here the definition of a loop. What's a loop? Well, a loop would mean that if you have a vertex and you have an edge where we allow that the edge is connected, so the vertex is connected to itself. In that case, well, this is a little bit strange. It's kind of an extreme situation, but you know there are many, many generalizations of graphs. And so sometimes this is allowed. You allow loops, Well, sometimes you don't. In that case, you call the graph loop-free. As I said, there are many generalizations. So for instance, there are also directed graphs. In that case, this is an ordered pair of vertices. So that means like your edge, it's important which way around you go. So usually this is just done by introducing arrows. So you use arrows. You have to say whether 1 goes to 2 or 2 goes to 1. If you do that, so you use instead of just edges, you use arrows. That gives you a directed graph. Also, that is very important in many applications we're going to talk about later. But for the moment, all of our graphs are usually not directed and have no loops. Okay, another really important definition is that of a subgraph. So what is a subgraph? Well, here's our graph G. And for instance, here's an example of something which is not a subgraph. So I abbreviate by this by as G. So why is this not a subgraph? Because there's an edge in here which hasn't been here before. So the definition is that the vertices of a subgraph consist of a subset of the vertices of the graph. And if there is an edge in the subgraph, that edge has also to be in the edge set of the graph. Now, here's a nice example. That is a subgraph. We see like that all these edges are here already, and we get an isolated vertex here. And this is actually also called a spanning subgraph. So what is a spanning subgraph? A spanning subgraph is one that uses the same vertex set. Uses the same vertices, so that is this definition, so please look it up again. So for instance, this one here was not a spanning subgraph because the vertex set 2, the vertex 2 was not in the vertex set of this. But anyway, this was not a subgraph in the first place. So where else? Yeah, here. Here for instance, here we see something which is a subgraph, but it's not spanning. Okay, and now there's one definition, namely induced, which is important. So what's an induced subgraph? Well, again, let's look at the picture, and then I think it should become clear. For instance, here, this is a subgraph. You can check this. Actually, it's not. I see that now, because I forgot to add this edge here. All right, so I hope this doesn't confuse. Anyway, we just changed this again. So this is now our graph. So I claim that this is now a subgraph, well, clearly, because that edge is now in there. Of course, I tricked a little bit. And now, so what does the definition induced mean here? Well, induced means that all the edges which are incident to vertices, to the vertex set of your subgraph, have to be edges of the subgraph. So for instance here, every edge connecting, let's say 1 and 4, or 1 and 3, which we have up here, is also in here. Now here is a subgraph which is not induced, because in this case, well, it is a subgraph, right? I mean, all the edges here come from above. But it's not induced because here the edge from 1 to 3, which is in the graph, is not in the subgraph. And so we write this usually in this form, so by just saying, okay, I pick a subset of the vertices, and now I get a subgraph which is induced by just taking all the edges which are incident only to vertices in here. So for instance, this one here, you would get that by writing 1, 3, 4, 5, because this is precisely the subgraph induced by just picking these vertices. Okay, and so please also look up these notions here. What happens if you take out a vertex of your graph? So this, think about it, look up the definition. This is not difficult at all, and in fact what it really is to take the induced subgraph on the vertex by taking all the vertices except that one vertex you want to take out. And also, you can define what happens if you take out an edge. Well, that is easy. You just remove one of the edges and everything else stays the same. So these are kind of very natural, important subgraphs. Okay, so let's go on with our definitions. So here's one with an interesting construction, that of the complement graph. So if you have a graph G, you also get a graph G bar. How does that work? Well, you choose the same set of vertices, but now the edges of G bar are precisely the edges which are missing in G. So, for instance here, this is our G. So what is G bar? Well, this has vertex at 1, 2, 3, 4, so this is also vertex at 1, 2, 3, 4. But now, the new edges are precisely ones which are not here. So 4, 3 is 1, 3, 2 is 1, 4, 2 is 1. But here, for instance, 1, 4 is an edge, so it's not here. And so if you now think about what happens if you go backwards, if you look at the complement of the complement, so the complement of the complement graph, well, what do you expect that you get? Well, by construction, you get just precisely G back. So here you get 1, 4, 1, 2, 1, 3, and so forth. Okay, and so what else? Well, we need also examples. A very important example is that of a complete graph. So a complete graph written Kn consists of n vertices, and now we use all the possible edges. So think about how many edges there are. That's something you should know how to do. So for instance, here is K4. We have 4 vertices, and now we connect them in all possible ways. So here, 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 and here. So this is not a vertex. And actually, just for the fun of it, let's draw it differently. So maybe here you're not sure if it's a vertex or not. Now you should be definitely clear what the graph is. And that's the same graph, because from an abstract viewpoint, we just know precisely which vertices are connected here or here. It doesn't matter. Okay, so this is an important graph. Now, a property. A graph is called bipartite if you have, you can partition the set of vertices in 2 parts. Both should be non-empty. So let's say the upper part here and the lower part. And the important condition is that all the edges you have in there are connect a vertex in the one set to a vertex in the other set, but never in the same of these 2 partitions. So we have these 2 partitions, these 2 subsets. So you're not allowed to connect this to this one here, and you not connect this to that one here or this to that one. We have these 2 subsets, and edges only go from one subset to the other. It's kind of, you separate them. But in between, there's nothing going on. There are no edges in between. So that's a very important property of a graph. And then there is the complete bipartite graph. Now, how do you get that one? So it's written KNM. Well, you take your 2 subsets, and you take, so these are n vertices now, these are m vertices, and you take all the possible edges under the condition that it should be a bipartite graph. So you're connecting this to that, to that, to that, to that, but to none of these. This to this, this, there, here, here, there, here. So I hope I didn't make any mistake. And this would be the complete bipartite graph. Again, think about how many edges it has. Okay. Very important, isomorphic graphs. So you sometimes have graphs which look different, but essentially they're the same graph. In that case, you call them isomorphic. So here's an example. So these are 2 different graphs. For instance, here 1 and 3 is not connected, while here 1 and 3 is connected. And so, I mean, these but in some sense, if you look at it, they really look kind of the same. So how do you make that precise? What is a graph isomorphism? Well, what you need is a bijection from a one vertex set to the other vertex set. So a 1-to-1 correspondence between the vertex sets. And I claim that this one here does the trick. So the vertex 1 goes to the vertex 2, the vertex 2 goes to the vertex 1, the vertex 3 goes to the vertex 4, and the vertex 4 goes to the vertex 3. Okay, so with one correspondence between the vertices. Well, you always find something like this if they have the same number of vertices. But the important property is that if you have an edge on this side connecting two vertices on this side, and then you go on the other side, and you want to know if the corresponding vertices in the other graph are also connected, then that should be true. So if they have an edge here, that goes to an edge there, and vice versa. Then you call it an isomorphism. So in this case, for instance, 1 and 2 are connected. And so that means now we have to check if 2 and 1 are connected. Well, they are. What about 2 and 4? So 2 and 4 are connected here. So we check if 1 and 3 are connected. Yeah, they are. And so forth. And so what you really do here is to see it's like just a mirror reflection. But this has always to be, this is just like an intuitive argument. This is really the proof, because now you can check that every edge here goes to an edge there and vice versa. So these are isomorphic. And now why is so kind of convenient? Because that means we know they have the same vertex set. We know they have the same edge set, because every edge here corresponds to an edge there and vice versa. So they have the same number of edges. And everything else you can think about, every property, if that holds for the one graph, it will also hold for the other graph. So it's a big question and a very, very hard question to check whether two graphs are isomorphic. And that's an important question. Okay, so one thing which sometimes helps to distinguish two graphs, to see that they are not isomorphic, are vertex degrees. So what's the degree of a vertex? So you pick a vertex, its degree is just defined as the number of edges it is contained in. So for instance here, this little graph, this vertex here is incident to 2, 3 edges, so the degree is 3. So very easy. Well, what about a loop? If you have a loop, then we define the degree to be 2. So it's actually going out. Okay, so here's a nice example. So we have two graphs. Question is, are they isomorphic? I mean, they look quite different, but for instance, you could check the number of vertices are 6 here, and we have 6 vertices there. Here we have 9 edges, and here we have also 9 edges. So that actually looks already that they are kind of close to each other. So how can you distinguish whether they're not isomorphic? Of course, you can try to find a map and show that it's just not possible to do so. But there's a very fast argument. The argument is we look at the vertex degrees. So let's write here the degree of a vertex. So the degree here is 2. The degree here is 1, 2, 3, 4. 1, 2, 3. 3, 1, 2, 3, 4, 2. What about here? 2, 4, 2, 4, 4, 2. And I hope I didn't make any stupid mistakes. So in that case, why can they be not isomorphic? Because, for instance, we have here 2 vertices of degree 2, but here we have 3 vertices of degree 2. And that's not possible. With an isomorphism, we have a vertex and that is incident to so and so many edges. If you go to the corresponding graph, on the corresponding side to a corresponding vertex, well, it will also lie in the same number of edges. So the degrees have to be the same. And that means no matter where this goes to, no matter how you do such an isomorphism, there should have the same number of vertices of given degree, but we have 2 here and then 3 vertices of degree 2. Or you could say, well, here's a vertex of degree 3, but there is no such vertex on the other side. Clearly, they are not isomorphic. So there is a very important formula on the vertex degrees. So here it is. So what does it say? Well, you just look at all the degrees of the vertices. So for every vertex, you look at its degree, and you count these numbers just up. Okay, and so what you get is precisely you get twice the number of edges. So this relation between something which is kind of a global invariant, and something which is a local invariant, something which you stand at your vertex and look around, you can count and you find out. This relation is, because of this, very important and has lots of applications, so you have to know this. So what's the proof idea? Well, just take any graph you like. And so here's the idea. The idea is we look at every edge, and then we write a 1 on each vertex it contains. So we were here on this edge, now let's go to that edge. So here another 1, here 1, now we go to that one here, 1, 1, we go to that one here. So, wait a second, yeah, so another one here and another one there, now we go to that one here. And here, and I really hope I didn't make any mistake. So, how many 1s do we have? Well, for every edge, we just wrote 2 1s there. So we have twice as many 1s as there are edges. So this is that number on the right. On the other hand, what do we notice? We notice here are 2 1s, and the degree of that vertex is 2. Here we have 3 1s, the degree is 3. Here the degree is 2, here the degree is 4, and here the degree is 1. Of course, that's no coincidence because by going over all the edges, we just precisely for each vertex that get so many 1s as there are edges, it is incident in. So the same number which we just computed on the right is just the sum of all the vertex degrees. And that's the end of the proof. Now, as I said, there are lots of applications. So here's a nice one, namely, the number of vertices that have odd degree is always even. So how can you prove this? Well, let's use our formula, of course. So let's look at the left side and the right side. So the left side, we go over all the vertices that just split them up in those where the degree is even, plus those where the degree is odd. Okay, so we sum over all the degrees of the vertices, but we split them in 2 sums. The ones where the degree is even, the ones where the degree is odd. And we know that this has to be twice the number of edges. So let's look at this sharply. And okay, so you see, so this is definitely an even number. What else? Okay, so these degrees are even. We sum over even numbers. That means if you have an even number plus something, so that is equal to an even number, that something has to be equal to an even number minus an even number, so it's an even number. So we conclude that this here, this sum, is also even. But what are we summing up? We are summing up odd numbers. So if you have odd numbers and you want to sum them up so you get something even, you better should sum up an even number, not an odd number of these. Because if you sum up an odd number 3 times, well, you get something, so odd plus odd gives even, plus odd gives odd. So that's not what you want, so you need like an even number of these odd numbers. So the number of vertices of odd degree is even. So here's a nice little, well, and really a little bit more challenging problem, for which I say you have to use this application we just seen, namely the following. What you have is you have an apartment, so just 1 floor, so like here, and you look at its floor plan, and the apartment has only 1 outside door, okay, only 1 way outside, right here. And then you look at this plan and you see all these doors for the rooms. I hope you can see this. And I claim, in any case what you will notice is there will always be one room, at least one room, exists some room which has an odd number of doors. Okay, so for instance here this has 2 doors, 2 doors, 2 doors, that is actually 2 doors, that is 2 doors, 2 doors, this one here has only 1 door. That's an odd number. So no matter how you do this, there will always exist a room with an odd number of doors. So I find that is a really nice problem. Also look up the definition of k-regular graphs. It's very easy. It just means that every vertex degree is the same. Think about some nice examples and play around a little bit to see whether there always exist these guys or not. And try to prove that there is no 6 regular graph with 32 edges. And you can already guess what you need, which immediately follows from this formula. So this is the formula you want to use here. Okay, so let me go a little bit to the side so you can see this table. That table is also in the book. And this is the table of walks. So what does it mean? Well, here we have our example graph. And what you do is you just walk from a vertex to another vertex by going along the edges. And so if you do that, in general this is called a walk. It's an open walk. If, for instance, you go from 1 to 4, going here along here. And it's a closed walk if you end up where you started at the beginning. And now we have different kinds of walks. So not only open and closed, but also maybe you don't want to use some edges again. So if you used one edge, you're not allowed to use it again. In that case, if it's open, it's called a trail. And otherwise, if it's closed, it's called a circuit. And here are all these examples, so try to play around and do this on your own. For instance, you could go from 1 to 2, 3 to 4, and then you could go to 1 again, and then 5, and then 3. And, well, in that case, for instance, you have no chance, you have to use an edge again. So that is not wouldn't have been a trail. So look at these examples I wrote up here, or try to play around with this on your own. This is not hard, it's just definitions. Well, the best thing you can do is if you go and you not only don't use edges again, but you also don't use any vertex again. Don't pass over a vertex again. That is a path. So you really always just use different vertices all the time. If you do that, then that's a path, and if you even close up, then it's called a cycle. And so these are, of course, very important notions. So there's not a lot of things to say about this. Think about why the table is complete. And here's a little exercise. You also find that in the book. So if you can walk from A to B, maybe you're using some edges again and again, or you maybe use some vertices again. You can always do that just by a path, because you can just leave out edges. If you use them already, you can just cut that out. So this is a nice little exercise. Try to think about, while if you walk around and you find some way to go from one vertex to another vertex, while you actually can always find one which is the shortest one, in some sense, which will then be a path. So it won't use vertices again. Because if you think about it, if you've been already at the place and then you go on, why don't you immediately go on to the next vertex? Why do you use that detour? That's the idea. So look at examples. This is really something you get immediately a very good intuition for this if you really look at some examples. Well, important definitions here: connected graph. A graph is connected if you can always go from one vertex to another vertex. So for instance, if it would be like here 6 and 7, then this would not be a connected graph because you cannot go from 3 to 6, for instance. And also where this immediate needs yields the notion of a connected component. So what are connected components? These are just the largest connected subgraphs you can have here. So for instance here, this graph has 2 components, 2 connected components, the one here and the one there. So this is a connected subgraph, this is one but you cannot go from one to another. And so every graph just splits up in these connected components, and the number is sometimes called kappa of G. So the amazing thing about graph theory is that it really grew out of a very concrete problem, and not so long ago. So this was considered by Euler, namely the famous 7 bridges of Königsberg. So essentially, I mean, this is all simplified, but there are, like, this is how it looks from the top, and you have here certain islands, and this is like land, and you have 7 bridges indicated here. And the question was, is it possible to walk over all of it, crossing all of these bridges, but never using a bridge twice? Okay, so maybe going here, then maybe here, then here, and here, but then you cannot use that bridge. Okay, so if you try this, you will run into some problems. Now, this is where graph theory was invented, because this really helps us solve a problem, because we can reformulate it. So we introduce these vertices here. So 4 vertices. And now for each bridge we have an edge. Like this. And now we have our graph. And so we can reformulate this in our now modern terminology by asking whether this graph has so a walk that doesn't use an edge twice, means that this is what's called a trail. And so we're asking if there's a trail that uses all the edges. Or, if you want to have it closed, if there's a circuit, a closed trail, using all the edges, of course, just once. And so this has a very, very satisfactory answer. That is that theorem here, that if you have, so let's just assume the graph has no isolated vertices, then the graph has an Euler circuit if and only if, of course, the graph should be connected, and every vertex degree is even. So if and only if every vertex degree is even, this is easy to check when you can find some Euler circuit. And the condition for an Euler trail is that, again, it should be connected, and there are precisely 2 vertices of odd degree. And if you think about it, it's not hard to see that if you go from this direction to that direction, at least in the case of a circuit, but the other direction is a little bit, involves a little bit more work. And if you use these criteria, you can, let's just check this here. For instance, here, so that has vertex degree 3, 3, hope to do this right, 3, and here we have 1, 2, 3, 4, 5. So in fact, this looks really bad for that condition here, because, I mean, if I'm not mistaken, I don't see any vertex degree which is even, and here we have much too many vertices of odd degree. So let me just sketch a little bit the idea here for the condition 1. Just proof idea. So please have a look at these proofs. Well, if you have an Euler circuit, so you go around, you're never allowed to use an edge twice, but of course you can use vertices twice. Like this maybe. What do we notice? Well, since you always go into a vertex and you get out again, all of these vertex degrees are even. And these are all the edges. So that is the easy direction, from left to right. Now what about the other way around? So this gets a little more sketchy, really just to convey some ideas here. Well, in that case, so we know now that every vertex degree is even, and it's connected. Now, if every vertex degree is just 2, means that whenever you have a vertex you can get in and out, then in that case, you will close it up like this. But since it's connected, you cannot go somewhere else because you assume. So I'm just assuming that every vertex degree here would be 2. And so we just close up and everything's fine. So this means we can kind of assume that there is at least some vertex, I don't know, maybe here, which has larger degree than just 2, maybe 4, or even more. And now what you do is you kind of use some kind of induction. You kind of remove these edges here. The edges we found by essentially just going around from a vertex. So we just start at the vertex, go around like this. But now we have a vertex which has larger degree. Well, anyway, what we do is we use some kind of induction. We remove the edges. And now the graph is not connected anymore, probably. But it will split up in several connected components. And then you use, for these connected subgraphs, you use the induction hypothesis that, which we know for smaller number of edges. Namely that, so for smaller graphs, that in this case it has an Euler circuit. So for every sub-component it has an Euler circuit. And so for instance, this means maybe here is one. Like this. Maybe that vertex here lies in one of the connected components. And maybe another one here. And so what you do is now, we add now again in our edges. And the idea is now you first go along this circuit, going through all these connected components, and then you go to the next vertex and do that same there, use this circuit, Euler circuit, and then you go to the next one. And of course, there are many cases you have to consider here. But at least the idea here is use some induction and then use the fact that a graph, if it's not connected, splits up in connected components. Find there the Euler circuits and then somehow put them all back together again. Okay, so this is very sketchy. So please read this about this in the book. Okay, what else? Try to do that little exercise here. What about the complete graph and complete bipartite graph? Do they have Euler circuits or Euler trails? What are the conditions there? And look at these examples in the book and look up the proofs. Even if you might not understand every detail, it's very good to get an idea of what is really going on here. It really allows you not only to, just look at this and say, okay, but really understand, try to be really close to get closer to this subject. Okay, so see you next week.